Every single time you see a new tweet or a DM or even a new user pop up on your feed, a tiny invisible miracle is happening. A totally unique number, an ID, is being born. Today, we're going to break down one of the most brilliant solutions to a massive internet problem, the Snowflake ID.
So let's just think about this for a second. Picture thousands of tweets being fired off every single second. They're coming from different servers, in different data centers, scattered all across the globe. How in the world do you make absolutely positively sure that no two tweets ever get the exact same ID number? And how do you do it without slowing the whole thing down to a crawl? That, my friends, is the big question.
At its core, this whole thing is what engineers call the distributed ID problem. You see, the way we all learn to count, 1, 2, 3, that works just fine if you've got one person doing the counting. But what happens when you have thousands of computers all trying to count at the exact same time? Well, you get chaos.
And you can see the problem right here on the screen. On the left, with just one server, everything is neat, it's ordered, super simple. But look at the right. In a real-world system, 3 different servers could all try to assign ID 1 at the exact same time. That's a collision, and for a database, that is an absolute disaster. It's just not allowed to happen.
So before the engineers at Twitter could even think about building something, they had to sit down and define the rules of the game. They had to figure out what a perfect idea would even look like. They came up with this really strict set of rules, kind of like a mission checklist that any idea would have to pass.
All right, rule number 1, size matters. The entire ID, the whole thing, has to fit inside a 64-bit integer. Now that's a pretty standard and efficient data type in programming, but it puts a really hard limit on how much information we can cram inside. And then there's speed. And wow, this one is a doozy. The system has to be able to spit out over 10,000 unique IDs every single second. And that's not like a peak number, that's just the baseline to keep the lights on. It's incredibly fast.
So here it is, the full mission checklist. On top of being unique, 64-bit, and super fast, the IDs have to be just numbers, no letters, no weird characters. But the real kicker, the one that trips up almost everyone, is this. They must be sortable by date. An ID created later has to be a bigger number than an ID created earlier. That sounds simple, but it's the toughest rule of all. Let's see how the other ideas stack up.
And this brings us to what I like to call the Hall of Almosts. These are all the common, really smart approaches that people tried first. They're good ideas, they make a lot of sense, but as we're about to see, each one of them stumbles on one of our crucial rules.
First up, we have multi-master replication. Now, the idea here is actually pretty clever. If you have, say, 3 servers, you just tell server 1 to only use numbers like 1, 4, 7, you get the idea. Server 2 will use 2, 5, 8, and so on. They each have their own lane, so they never step on each other's toes.
But here's the deal breaker. It completely fails our sortability rule. An ID like 8 from server 2 might actually be created after an ID like 7 from server 1, which totally breaks the chronological order we need. Plus, trying to add or remove servers is a massive headache, so this one's out.
Okay, next up is the UUID, or Universally Unique Identifier. You've probably seen these before. They're those long strings of letters and numbers. They're 128-bit numbers generated using things like the server's network card and the exact time, and the odds of 2 computers ever generating the same one are, well, they're basically 0.
So you'd think this is it, right? Problem solved. Well, not so fast. UIDs are fantastic for being unique, but they fail 3 of our rules. They're way too big, twice our 64-bit limit. They can have letters in them, and, critically, they are not sortable by time. So, another almost.
Our final contender is the ticket server. This is maybe the simplest idea of them all, used by sites like Flickr way back in the day. You just have one central server, and its only job is to hand out numbers. You need an ID, you just ask the ticket server, and it gives you the next one in line. It's literally like taking a ticket at a deli counter.
Now this approach gets you perfectly ordered numeric IDs. It seems great, but it has a fatal flaw, a single point of failure. If that one ticket server goes down for even a second, the entire system, every tweet, every message, grinds to a halt. For a service that has to be on 24/7, that's just a complete non-starter.
So, after seeing all the ways it doesn't work, we finally arrive at the solution that does, and it required a totally different way of thinking, a new approach developed at Twitter called Snowflake. And yeah, it's named that because just like a real snowflake, every single ID it creates is guaranteed to be one of a kind.
And this, right here, is the light bulb moment, the genius of the Snowflake approach. Instead of trying to get thousands of servers to agree on one single count, they decided to pack all the information they needed for uniqueness inside the number itself. You can think of it like a car's VIN number, where different parts of the number tell you who made it, where it was made, and what year it is. It's a number with a story.
So how does this actually work? Let's crack the code. Let's look at the anatomy of this smarter number. We're going to break down that 64-bit ID piece by piece, and you'll see exactly how it manages to check every single box on our list. Here it is. That 64-bit number isn't just one random number. It's actually a package of 4 different pieces of information, all cleverly combined. A timestamp, a data center ID, a machine ID, and something called a sequence number. Let's break those down.
Okay, the biggest piece by far, a whole 41 bits, is the timestamp. This is the secret sauce. It's just the number of milliseconds that have passed since a specific date back in 2010. By putting the time first, it means the IDs are automatically sortable. A later time always means a bigger number. Boom. That one trick solves our biggest problem, and it's got enough room to work for about 69 years.
So, what about collisions between servers? Well, the next 10 bits take care of that. 5 bits are for the data center ID, and 5 are for the machine's ID within that data center. This basically gives every single server its own unique address. It makes it literally impossible for a machine in one part of the world to create the same ID as a machine somewhere else at the same time.
But you might be asking, what if one super fast machine needs to create multiple IDs in the exact same millisecond? That's what these last 12 bits are for. It's just a simple little counter that ticks up from 0. This allows a single machine to generate over 4,000 unique IDs in a single millisecond. That's how it gets its incredible speed.
So there you have it. The timestamp gives us order, the machine IDs give us uniqueness, and the sequence number gives us speed. Snowflake checks every single box on our list. It's an incredibly elegant, really beautiful solution. But the story doesn't quite end there.
Does this mean the problem is solved? Perfectly? Forever? With no downsides at all? Well, as you can probably guess, it's not quite that simple. This brilliant design actually introduces its own new, more subtle challenges that engineers have to deal with.
And this really is the ultimate takeaway. The whole Snowflake ID system depends on every server's clock being perfectly in sync. If one clock drifts even a little bit, the IDs could go out of order. Now, that's a solvable problem, but it reveals a fundamental truth about engineering. There are no perfect answers. There are only intelligent trade-offs. You solve one massive problem, and in return, you get a few smaller, more manageable ones. And that right there is the constant, fascinating cycle of innovation.